So we have our interpretation of vectors as arrows in space. Let's now see how the operations we've developed connect with those geometric ideas. I want to start with a theorem, and this is going to be the first theorem that I prove in this course. And this theorem says that if we scale a vector v by a number c, and then we take length, this is always the same thing as the absolute value of the scalar we used multiplied by the length of the original vector. So we have a formula we want to prove, and I want to walk through this proof line by line here. So how does the proof work? Well, I'm looking at the length of a scalar c multiplied by a vector. By definition, well, what are we doing? We're scaling our vector by the scalar, and let's say that the coordinates of our vector are v1, v2, up to vn. Well, what the formula for scaling says, all we have to do is scale each one of these coordinates, v1, v2, up to vn, by the number c. And now, by definition of length, what we're doing is we're summing the squares of all of these new scaled coordinates. So we're looking at the quantity c times v1 squared plus c times v2 squared, and so on and so forth, all under a radical. And if we remember how squares work, c times v1 squared is the same thing as c squared times v1 squared, and c times v2 squared is the same thing as c squared times v2 squared, and so on. So we can factor out a c squared from this expression here, and we're left with the square root of c squared multiplied by the quantity v1 squared plus v2 squared up to vn squared. And remember, radicals do not distribute over addition, but they do distribute over multiplication. So this is the same thing as the square root of c squared multiplied by the square root of the sum of the squares of the original vector v. And it's tempting to say that the square root of c squared is just c, but when we square our number, we end up forgetting whether or not the original number was positive or negative. So the square root of c squared is actually the absolute value of c. And we'll recognize here the square root of the sum of the squares of all of the original coordinates of v as the length of v. And this proves our formula. So the punchline here is that if we're interested in the length of a scaled vector, the idea is that we should look at the length of the original vector and then scale that length by the absolute value of our number. This is a connection between arithmetic and geometry. So this slide has no good pictures. Let's look at a slide that has some pictures. So here's the idea. When we scale a vector by a number, the idea is that we end up scaling and orienting our vector. So let's say that the vector we're interested in is this blue vector here, v. Well, what should 2 times v look like as a geometric object? Well, it should just be the same vector, except we should stretch the length by a factor of 2. That's what the theorem says. What should 1/2 times v look like? Well, 1/2 times v should be the same vector as v, except we should scale the length by 1/2, which is to say we should shrink the length by a factor of 2. What about negative numbers? Well, what about negative 1/2 times v? Well, this should be the same vector as v, except since we're multiplying by a negative number, we need to reverse the direction of the arrow. And since the absolute value of this number is 1/2, we should scale the length by a factor of 1/2 or shrink by a factor of 2. What about negative 1 times v? Well, since the absolute value of negative 1 is 1, this should end up not changing the length of our vector at all, but negative 1 is a negative number, so this should simply reverse the direction of the arrow. So the idea here is that the absolute value, or the magnitude of the absolute value of the scalar we're using to scale our vector, controls the length of our vector, while the sign of the scalar controls the direction of our vector. So we have this nice connection between the arithmetic of scaling and our geometric interpretation of vectors as arrows. What about addition? This one's my favorite. So let's say we want to interpret v plus w geometrically. Well, the first thing we do is we start with our vectors v and w, and then we form a parallelogram from these vectors. Remember, vectors don't inherently care about location, so you can replicate the same vector wherever you want. Well, I want to put another copy of this vector v in such a way, in the figure in such a way that it emanates from the tail of W. And then I want another copy of W positioned in such a way that it emanates from the tail of the original V. So now I'm looking at a parallelogram. Here's a cool interpretation of vector addition. Vector addition, so the sum of V and W, turns out to be the diagonal of this parallelogram. So the sum of V and W ends up being the vector in red here, which starts from the same position that V and W originally started as, and that points at the other opposite vertex of the parallelogram we've just created. So vector addition is sort of encoded geometrically in the sides of this parallelogram. So the idea is like to start where V plus W starts and to end where V plus W ends, we have two paths. We could either go through V and then through W, or we could go through W and then through V. That's the same thing, which is really a geometric proof that V plus W is the same thing as W plus V. And even though it might seem like we're just playing games here, this will turn out, and we'll see this later in the course, that this will turn out to have utility. So sometimes we'll find ourselves in a situation where we're looking at a diagram where there's lots of components to it. So there's lots of different vectors pointing in different directions. And sometimes it's useful to figure out how some of those vectors relate to one another. So here what we're looking at is a diagram where I have a bunch of different vectors pointing in a bunch of different directions. And let's say here that I know what the vectors in blue are. So I know X, I know V, and I know W. But let's say that I'm not so sure what the vectors in red are. So maybe I don't know what Y is, and I don't know what Z is. Well, the idea here is that I can figure out formulas for Y and Z with vector arithmetic. So here, let's look at Y. Y is starting at the place where X terminates, so at the tail of X, and Y terminates at the tail of V. So the idea here is that, well, there's really two paths to get from start to end as far as Y is concerned. We could just go through Y, but the idea is that I don't know what Y is, so I could take an alternate route. I could go against X and then with V. So what this suggests is that Y is actually equal to V minus X, because to get from start to end, we went through negative X and positive V. Let's look at the vector Z here. To get from start to end, our alternate path here would be with W and then against V. So this is suggesting that Z is actually equal to W minus V. So learning how to manipulate or interpret these diagrams can sometimes be useful for us, especially in situations where we know lots about certain vectors in the diagram, but know less about other vectors in a diagram. Our next adjective that I'd like to cover in terms of vectors is the concept of a unit vector. These will play enormously crucial roles later in the course. So a unit vector is a vector whose length is equal to 1. So here's our first example of a unit vector. This is the vector u, and this vector is a vector in R4, and the coordinates here are 1/2, -1/2, -1/2, 1/2. Let's calculate the length of this vector. So the length of this vector is the length of this, the coordinates 1/2, -1/2, -1/2, 1/2. Here's a trick that I like to use when I'm dealing with vectors like this. I don't want to have to add a bunch of 1/2s and mess around with that because I'm bad at fractional arithmetic. So instead what I'm going to do is I'm going to factor out the 1/2 from all of the coordinates. So now I'm looking at the length of the vector 1/2 multiplied by 1, -1, -1, 1. And as we've seen before, we can factor out scalars from lengths in absolute value. So now I can factor out the absolute value of 1/2 from my length calculation here. So now I'm looking at the length of the vector 1, -1, -1, 1. Well, the length of the vector is the square root of the sum of the squares of the coordinates. So remember, the absolute value of 1/2 is just 1/2, so I didn't even need absolute value signs here. And now I'm looking at the square root of 1 squared plus -1 squared plus -1 squared plus 1 squared, which is really just the square root of 1 plus 1 plus 1 plus 1, which is the square root of 4. which is equal to 2. And since I'm multiplying by 1/2, this turns out to equal 1. So this is our first example of a unit vector because the length of this vector is equal to 1. So this is essentially the proof, so to speak, that this vector is a unit vector. Another important construction is the construction of the normalization of a vector. So the normalization of a vector v is sometimes referred to with this hat notation, so v hat here. This is a little bit unfortunate because later in the course we're going to use hat notation to refer to something different, but for now we'll use hat notation to refer to the normalization of a vector. And by definition, this is the same as the original vector, except we scale by 1 over the length of that vector. So if you want to get a sense for what we're doing geometrically here, let's just say for a moment that our vector v is really long. Let's say it's very long. Well, when we scale by 1 over the length, if the vector is really long, 1 over the length is really small, so the idea is that maybe we're shrinking the vector to obtain the normalization. Obviously, the opposite would be true if the vector was really short. If we divide by a really small number, we get a really large vector. So if the vector was short, we'd end up making it a little longer. But if you think about it, if we're taking really long vectors and making them short to some degree, and we're taking really short vectors and making them longer to a degree, the question is, well, to what degree? Well, we could calculate that ourselves. So what is the length of the normalization? Well, this is the length of 1 over the length times the vector. And 1 over the length is a scalar value, so we can factor that out of our length computation and then multiply by the length of v. But we don't need an absolute value sign here because lengths are never negative. So this is really 1 over the original length of v multiplied by the length of v, which of course is equal to 1. So the punchline here is that the normalization of a vector is always a unit vector. So if you like this is useful sometimes, let's say like you and I are having a conversation about some displacement vector. Maybe I'm using a vector that's like really short and you're using a vector that's really long. One thing we can do to standardize our conversation is just normalize our vectors, and now we're talking about the same unit vector. So this turns out to be an actually important construction. So here's an example. So here I have a vector v in R4, so we have 4 coordinates here. If I bothered to calculate the length of this vector, I would sum the squares of the coordinates and then take a square root. So I would take 9 plus 64 plus 16 plus 4, take a square root. That's the square root of 93. And how would I use this length to calculate the normalization? Well, I would take 1 divided by that length, so 1 over root 93, and just multiply by the original vector. I'm guaranteed that this vector v hat is a unit vector because it's the normalization of something. So once again, we find that the algebra that we're working with allows us to speak geometrically about this particular vector, which happens to live in 4 dimensions. So we're happily speaking about geometry of dimensions that we can't even really see.